Inshallah, in this lab session, we are going to do experiment about determination of heat of neutralization. That is delta H of neutralization for the reaction of acid with base. And we are going to make two solutions. These are dilute solutions of acid and base. are going to mix them, make these two solutions react with each other, okay? And then we calculate what we say, or we determine what we say here, delta H. Delta H is the enthalpy of formation. Enthalpy of formation, you are going to determine what is the difference in the heat content of the product from the heat of contents of the reactant. So what we expect here, that delta H for this reaction, or any chemical reaction in general, either it is negative or positive, means the whole process or whole chemical reaction is either exothermic, when in that case the reaction will produce heat, or it is endothermic, and in that case the reaction will absorb heat. So we are going to mix two solutions, acid and base. If we mix equimolar volumes of these two solutions, HCl and NaH, what we get only H2O and salt, and plus heat if delta H is negative, okay? And plus heat, it means if the reaction is exothermic, so what we expect with the product, also heat is released, and in that case delta H will be negative. But if we mix both and the solution becomes cold, in this case delta H is positive and the process or the chemical reaction is endothermic, so it has absorbed heat. Now the heat exchange is going to be between the system, which we are studying here, and the surrounding. Now theoretically, as we are going also to learn, that delta H is equal to QP. Delta H will change in enthalpy. What enthalpy? We have HCl and NaH reacting with each other, so they have heat content, and we have H2O and HCl produced, and they have heat content. Now the difference between the H of the product from the H of the reactant will give you delta H. Now delta H experimental, it's equal to Q at constant P. Q, heat. And the unit of the heat, either calorie or joule, as we are going to handle in the laboratory. Now delta H is equal Q at constant P. What do you mean by constant P? This chemical process, or this chemical reaction, we are going to perform under constant pressure. There will be no change in pressure during the chemical reaction. So pressure is constant. When the pressure is constant, delta H becomes equal to Q. Now Q equals what? M X S X delta T. M is the mass. It's going to be the mass of the solution. After mixing HCl with NaH, you are going to get a solution that is a neutral solution. That's why we say it is heat of neutralization. So M is the mass in gram. The unit of mass here is the gram. S is the specific heat. What is specific heat? Specific heat is the heat Q needed to raise the temperature, T capital, of 1 gram of a substance by 1 degree Celsius. This is what we call specific. Now, delta T is the change in the temperature. Where does this change come from? Come from the temperature of these two solutions before mixing and the temperature of the solution after mixing. If this reaction is exothermic or endothermic, if this reaction is accompanied by heat exchange, then definitely delta E is going to be greater than 0. So what is the temperature of the solutions before mixing? This is T1. What is the temperature of the solution after mixing? This is T2. So T2 minus T1 makes delta T. Now from delta T and the specific heat given, or that is of water usually, which is equal to 1 calorie. Let's say 1 calorie per 1 gram degree Celsius, and this is the mass. What depends on the mass of the solution, how many or how much of the solution taken, or the amount of solution taken in this chemical reaction. So this is easy. So if you want to determine delta H for a chemical reaction in the laboratory, and simple chemical reaction like this at constant P, then you have to determine delta T, because as is theoretically known, M is how much of the solution you have taken or produced. Now Q will be equal to delta H as long as the reaction is under constant pressure, and then delta H can be simply known for this chemical reaction. Now we are going also to determine what we call heat capacity. Q, that is either joules or calories, needed to raise the temperature of an object by 1 degree Celsius. What object we are going to use in the laboratory today is the calorimeter. احنا جبنا 2 beakers, we made the insulation. These are 2 beakers into each other with a tissue paper inside. Okay. Now these are, let's say, insulated. Okay. This is, we are going to call a calorimeter, a device used to determine the temperature. Here we are going to determine the heat, or the heat content, experimentally heat. Now this is, I'm going to call calorimeter. I'm going to use this device. Now if I want to use this device, my calorimeter, then I have to find the heat capacity for this. And what is the heat capacity for this object? Is the heat needed to raise the object temperature by 1 degree Celsius. Now experimentally, I'll show you how we are going to perform this experimentally. Lab exercise number 6, today's experiment. I'll show you how we are going to determine delta H. Now delta H will be, inshallah, found by calculation. But what exactly the experiment is about? Experiment is about measuring temperature. From measuring temperatures you can find the Q, and from Q you can find delta H. Experimentally, what you will do is just simply you will note down the change in temperatures. So this is what the whole experiment is about. Now I have calorimeter, beaker, and then since I want to start by calibrating the calorimeter, means I want to find what is the heat capacity of this calorimeter. C. What is the heat capacity of this? How much heat is needed to raise the temperature of this object by 1 degree Celsius? So I have the calorimeter and simple beaker. And I have a digital thermometer. Okay? Okay. First of all, I'll start by taking water in 1 beaker. This water which I've taken now in the beaker is cold water. And now I'll be taking hot water. I'll measure the temperature of the cold water first. I'll take 25 ml in the calorimeter, and I'll take another 25 ml of hot water in the beaker. I'll measure the temperature of the cold water and the temperature of hot water. Then I'll pour the hot water on the cold water. Okay? And then I'll measure what is the maximum temperature reached by the cold water. Now I'll take a beaker. I'll fill this beaker with hot water. Okay? And I'll take 25 ml cold water by measuring cylinder. I will add this 25 ml cold water inside the calorimeter. Okay, and I'll start the temperature. Let's see, find my digital thermometer will report the temperature of the cold water, which is in the inside the calorimeter. Now I will wait some time. So it's giving a temperature now. Now temperature is fixed. I can report this temperature in my lab manual. Then I'll show after some time what is the. Now, I'll take 25 ml of hot water. I'll put this 25 ml of hot water in the beaker. Okay. Now, since I reported the temperature of the cold water, I'll put the thermometer inside the hot water. And I'll wait till the temperature is not changing anymore or not increasing anymore. And then I'll report the temperature of the hot water in my lab manual. Let it fix. Doesn't change anymore. Now it's still increasing. And I will. Now I report the temperature of the cold water and the temperature of hot water. After I report them, okay, now temperature is not changing. So what I'll do, I will add the hot water on the cold water inside the calorimeter. What? There will be a decrease or drop in the temperature of the cold water with the hot water. And there will be increase in the temperature of the cold water. Now, I'll see that we have reached up to temperature. You'll hear the temperature after mixing hot water with cold water. I report this one. Now I have three temperatures. One is the temperature of the cold water, one is the temperature of hot water, and one is the temperature after mixing hot with cold. So three temperatures. I reported these three temperatures. Okay? I'll then show how we perform the calculation. Now this is my data, which I collect from the experiment, which I'm doing now. I'm not doing anything but measuring temperature, right? Nothing else. But now, why we are doing this? We are doing this experiment with the hot and cold water to determine the heat capacity of the calorimeter. Now, when you add hot water to cold water in a calorimeter, the temperature of the hot water will drop, right? And the temperature of the cold water will raise or increase. So, now, there is a difference in the drop than the increase. That difference is the heat absorbed by the calorimeter. So when you add hot water to cold water inside the calorimeter, the hot water will lose heat to the cold water and to the calorimeter. Now we will find out the amount of heat that is gained by the calorimeter. And then we divide it by delta T1 at temperature, and then we can find the heat capacity of the cold water. Sorry, heat capacity of the calorimeter. Then I'll move to part P. Part P is our reaction. We want to find delta H for this reaction. Then the same calorimeter, now the calorimeter which I use, or which I determine heat capacity for it, is going to be used in part B, same one. So, what I'll do, I'll just pour the water, okay? Now this is my calorimeter, and this is my beaker. Now I finish from hot and cold water. I don't need them anymore. Khalas. Now when I do some calculation here, I'll find what is the heat capacity of the calorimeter. Now I'll bring acid, base. These are dilute solutions, not concentrated one. And then I'll take base 25 ml. cylinder. And I'll put this one in the beaker. I'll put the probe. I want to measure what is the temperature of the basic solution NaH. Then, using another measuring cylinder, another solution that is HCl, I'll take another 25 ml. But this one, 25 ml of HCl, I'm going to keep inside the calorimeter. This is for HCl and this is for N. Now I'm going to report the temperature of NaOH. And also what I'll do, I'll report the temperature of HCl solution in the calorimeter. There will be minor changes are there, maybe 0.1, 0.2 changes. We are going to consider these changes, our temperature difference. That difference can be considered, and then we can say they are both almost giving the same temperature because both are kept at room temperature for a long time. Now see, both are having the same temperature. What I'll do, I'll report the temperature of HCl, temperature of NaH, then I will add NaH solution which is in the beaker on the HCl solution which is in the calorimeter, and then I will observe that there is increase in the temperature. What do this increase in the temperature mean? What does it mean? What does mean that after mixing the temperature has increased? Does it mean it is an exothermic or an endothermic process? It is exothermic process, right? Why exothermic process? Because mixing HCl with NaH produces heat. When it produces heat, the solution will, which is the surrounding, will absorb this heat. When the solution gain or absorb this heat, its temperature increases. Now see, now I am having the temperature of both the solution. Before they were 20.2, 20.2. Now after mixing the temperature is 24.8. 24.8 is the temperature of the solution produced by the reaction of HCl and NaOH. And the 20.2 was the temperature of HCl solution and NaOH solution before mixing. So my experiment is over. It is finished. Once I tabulate the data, okay, I start the calculation, and after I finish the calculation, I can find the TH. So this is the manual. The same experiment were performed earlier, and these are the data. Reported the temperature of cold water and hot water, the temperature of the water after mixing. Then I calculated the raising temperature of cold water and the drop in the temperature of the hot water. In the calculation, I calculated the heat lost by hot water, and also I calculate the heat gained by cold water. Delta T2 is 9 in my case. So I multiply this with the mass, which is 25, and then with the specific heat, which is 1. Then heat gained by the calorimeter is going to be the difference between the heat lost by the hot water and the heat gained by the cold water. After that, I divide this by delta T1, which is the change in the temperature of here, the rising temperature of cold water. Now I determine heat capacity. In part B, the temperature of solution and NaH solutions were reported. Then I've taken the average. Then I reported the highest temperature observed after mixing acid with base, and then I calculated the change in temperature. It was almost 4 degrees Celsius. Mass of sodium chloride solution is 50 grams. Now I did my calculation. I found the heat gained by solution, heat gained by calorimeter. I then sum both the heat absorbed by both the solution and calorimeter. Heat absorbed or gained by solution and calorimeter is the same as the heat produced by the reaction, but both have the opposite sign. Gain positive, release is negative. Then I determine how many moles of water were produced, which is 0.05. Finally, I calculated the delta H, heat of neutralization in calorie per mole, but then I converted it to kilojoule per mole, and finally it was found something around minus 20.9 kilojoule per mole. Thank you very much. Thank you very much.